Hey Calc BC, today we're going to be talking about lesson 7.3, Power Series. This is our third lesson and our seventh unit. And in College Board, we are again in the second half of their unit 10 here, specifically the 13th lesson, radius and interval of convergence of a power series. And you will know what both of those terms mean, radius of convergence and interval of convergence, as well as what a power series is by the end of this lesson. There's a whole bunch of essential knowledge listed by College Board. I'm not even going to read this to you because it won't mean too much until you see the visuals and see the notes themselves. So we're just going to jump into the notes and get started. All right, so here we go. 7.3, Power Series. The series first listed on this page is an infinite series that we could call a series of constants. This is something that is like most of the series that we looked at in the last unit, right? There's no x. N gets filled in for each one of these fractions, and therefore each one of these fractions becomes a constant. But some of the series we've looked at so far this unit have had x's, right? So the general term for any infinite series that has x raised to a power of n is a power series. And this specific series listed here is centered at x equals 5, just like we talked about with the Taylor polynomials. We're centered at a specific number. And the new piece to this is that we can have like a general term for our power series, which is listed right here. And that's what would show up in the series notation with the summation symbol. So the definition here is if x is a variable, then an infinite series in this form is called a power series centered at c, where c is a constant. So today, what we're going to be looking at is the radius of convergence and interval of convergence for a power series. Remember, power series, again, it's just when there's an x to some power n, that would then get expanded like so. So think of a power series as a function of x, like this, where the domain of f is a set of all x's for which the power series converges. Determining the domain of a power series is the primary concern of this section. So we really want to make sure you know what that means. So think about all the way back up here. We've got these two types of series of constants or a power series. Once I plug in a number for x, let's just say I wanted x to be 2. Now suddenly, this is a series of constants again, right? So what we want to figure out is what x values can I plug in to this power series that make the series of constants that result from it converge. And if I can plug in x and then the resulting series converges, then that x value is considered to be part of the domain. All right, so hopefully that clicked. We're looking for x values that make the series converge. It's not like we're going to be graphing this with the x and thinking about when the graph exists. We're going to be more interested in the sum converging or diverging. So anyway, let's just kind of keep going through some of this. So we are always going to be converging at the center, whatever c is. So think about that. If we kind of look at this definition here, I think about plugging in c for x. Almost all of these parentheses are going to be canceling out and equaling 0, and we're going to be left just with the first term. And you can see that down here, right? Even if we do c minus c to the 0 power, that's anything to the 0 power is 1. So we have 1 times a sub 0. So it's the first term. So plugging in 0 or whatever c is into the series is always going to be convergent. It's always part of the domain. So we've got this theorem, convergence of a power series. For a power series centered at c, precisely one of the following is true about the domain. And this goes along with the picture up here. So I'm going to reference that as we go. The series might converge only at c. So there's going to be some x value that we can plug in where we're centered, and any other x value might make it diverge. There might exist a real number, capital R, that's greater than 0, such that its series converges absolutely for absolute value of x minus c is less than r, and diverges for absolute value of x minus c is greater than r. And that looks like this, meaning that there's some capital R, and if I add or subtract that value from c, we get an interval where we converge, and everything to the left and to the right of that interval diverges. Or the series might converge for all real numbers. All right, the number capital R is called the radius of convergence of the power series. So we consider this R to be the radius. We don't have a circle, right? But it's still called the radius of convergence. Think about if we did have a circle here, the radius would go to the left and to the right of the center point. So that's kind of where that comes from. If the series converges only at C, we consider the radius of convergence to be R equals 0. So if it's just a single point, we could write R is 0. If it's an interval, we say that R is whatever that value is. And if the series converges for all x, we would say that R is infinity, because we could potentially add or subtract infinity from C and still get an interval where we converge, okay? So the set of all values of x for which the power series converges is called the interval of convergence. All right, there's a lot going on there. Got a little bit more to talk about, and then we're going to try this so that it makes more sense. The last thing is endpoint convergence. Note that for a power series whose radius of convergence is a finite number r, so that was that second case from the front, the theorem says nothing about the convergence at the endpoints of the interval of convergence. Each endpoint must be tested separately for convergence or divergence. Therefore, the interval can take any of the following 6 forms. The first 2 we saw on the other side of the page. The radius could be 0, so we just have a point at C. The radius might be infinity, so the whole number line of x values would make the series converge. Or if we have a radius r, we might not include either of the endpoints. We might just include the right endpoint. We might just include the left endpoint, or we might include both endpoints. We're going to use the ratio test to find the radius and the interval of convergence. We know what the ratio test says, but here it is stated again. And so let's try this. Find the radius of convergence and the interval of convergence. Be sure to check the endpoints. Note, every time you are asked to find the interval, you must check to see if the endpoints are included in the interval. So that's something we're going to have to do every single time. But let's just start by running the ratio test, right? So that's what we're going to try to do here. So I'm going to write a sub n. We should be able to tell is just, that initial statement, and we have an x in it this time, but we're going to include the x. N times 2 to the n. So we need to figure out what is a sub n plus 1 so that we can plug into this ratio test. So I'm just going to change all the n's to n plus 1s. And I'm going to make sure I don't change x, right? X is a different variable than n. We're only changing the n's to n plus 1. So this becomes -1 to the n plus 1 plus 1, or n plus 2. X minus 5 stays x minus 5. I only change the n to n plus 1. On the bottom, we have an n plus 1 now, times 2 to the n plus 1 power. All right, so let's try the ratio test. So I'm going to start that on the next line. We have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So I'm going to write this as a multiplication instead of a division. A sub n plus 1 comes first. -1 to the n plus 2 times x minus 5 to the n plus 1 over n plus 1 times 2 to the n plus 1. And then I'm going to multiply by the reciprocal of a sub n. And we'll see what happens. All right, so right away, I know that since I'm in absolute value, the -1 to the powers are not going to matter. So I'm just going to cross those out. And I'm going to figure out what else can I do here to get rid of some of the rest of these terms. I don't think I'm going to be able to get rid of this n or this n+1, but I can probably reduce the x minus 5s and the 2 to the powers. So I'm going to rewrite this in a way that allows me to cancel some more things out. So x minus 5 to the n+1 is the same thing as x minus 5 to the n times x minus 5 to the 1. We're stuck with the n, we're stuck with the 2 to the n. On the bottom, we're stuck with the n+1. I'm going to change 2 to the n+1 to 2 to the n times 2. And we're stuck with the x minus 5 to the n. So now what can cancel? We have a 2 to the n and an x minus 5 to the n. And I think that is it. Yeah, so we have the limit as n approaches infinity of x minus 5 times n over n+1 times 2. And what we want to do here is try to separate the x portion from the n portion, if possible. And lucky for us, this n right here is not an exponent. So the x minus 5 can kind of come out. So what I'm going to do is I'm going to write it as the limit as n approaches infinity of the absolute value of n over, and I can leave the 2 in there, 2 times n+1 times the absolute value of x minus 5. So what I'm doing is separating the x portion from the n portion, because this limit only tells me that n is approaching infinity. It doesn't tell me anything about x. So now I'm just going to evaluate this limit. And since I have same exponent on top and on the bottom, same degree, it's going to approach 1 divided by 2. So this is now equal to 1/2 times the absolute value of x minus 5. 1/2 is already positive, so I didn't need to keep the absolute value bars. And we get to the end of the ratio test. So what does the ratio test say? I've never had an x in my ratio test before, but the ratio test says that a series will converge if this whole limit is less than 1. So we want this answer to be less than 1. So we want 1/2 times the absolute value of x minus 5 to be less than 1. So when is that going to happen? Well, I can multiply 2 on both sides and we get x minus 5 has to be less than 2. And that's sort of where we're going to pause because we were initially centered at 5. We had x minus 5 in our original statement of the series. So we know that x minus 5 is less than 2. That's telling us that this is our r. Now, if we wanted to go a step further, we could. You need to remember that absolute value means that we really have -2 is less than x minus 5 is less than 2. That's kind of how you expand that to get rid of the absolute value. And then we would add 5 to all 3 sides of this inequality. So we would get x is less than 7. And on this side, what would we have? 3. So we know that x has to be between 3 and 7. But an easier way to do this in the future would just be to stop when you get to the point where you have your x minus 5 from the original. The 2 becomes your r. And then all I have to do is add 2 and subtract 2 from 5 to get the bounds. So if we do 5 plus 2, we get 7. We do 5 minus 2, we get 3. So in other words, it's 5 plus 2 and 5 minus 2 to get the bounds of our interval. So we are getting close here. Remember, our final answer is going to be to state a radius of convergence and an interval of convergence. And these are going to tell us the x values that make this series converge, right? It's going to be what x values can I plug in here to make this series into something that magically converges versus other x values that would make the series diverge using all the tests from our previous unit. So let's see here. So right now we know the radius of convergence is r equals 2. That part's already done. So that means since we're centered at 5, we add 2 or subtract 2 from 5 to find the bounds of our interval of convergence. So our interval is going to go from 3 to 7. I'm going to write that in interval notation. The problem is, if you're tracking with us, I don't know if I should put parentheses or brackets for the 3 and the 7. Remember, back up at the top of this page, we said if the radius is r, in this case it's 2, there's 4 different possibilities. Every endpoint can be either a bracket or a parenthesis. It can be included or excluded. So what we have to do now is legitimately try the 3 and the 7 to see if they make this series converge or diverge. So I'm going to put a little line here so I can use this space. So this is where I'm going to try x equals 3. So I'm going to go back to the beginning and plug 3 in for x and see what happens. So we have the series from 1 to infinity, -1 to the n plus 1, 3 minus 5 to the n over n times 2 to the n. So it's very important that we keep track of that. I'm plugging 3 in for x, not for n. So this time we are plugging in for x. And okay, so let's see what happens here. We have 3 minus 5, which is -2. So I have n equals 1 to infinity, -1 to the n plus 1, -2 to the n over n times 2 to the n. This 2 to the n and the -2 to the n can combine since they have the same power. So we end up with -1 to the n plus 1, and -2 divided by 2 is just -1. So we end up with -1 to the n all over n. And -1 to the n plus 1 times -1 to the n. Let's think about what that's going to be doing here. It doesn't matter what n I plug in. One of these is always going to be equal -1, and the other one's going to always equal +1. So combined together, this just equals -1. Or we could do n plus 1 plus n, so we would get 2n plus 1, which is always going to be odd. Anyway, the point is that this just becomes -1 over n. And the -1 could be pulled out in front since it's a constant, so we really have 1 over n. So this diverges because it is the harmonic series in disguise. If you think back to last unit, the harmonic series, it's a p series with p equal 1. And that makes it diverge. Okay, so what we know now is for our interval of convergence, we're not going to include the 3 because the 3 made the series diverge. So then we're going to check the 7, the other endpoint. I don't have much space left, so hopefully this will fit. So now we're going to go back to the original series again, and this time plug in 7 for x. So we have -1 to the n plus 1 times 2 to the n over n times 2 to the n. The 2 to the n's just cancel out this time and leave us with, oh my gosh, I forgot my summation symbol. Don't be like me. Okay, so now we get -1 to the n plus 1 over n. This time, we have a series with 1 over n, and it's alternating. So this is going to converge because it's the alternating harmonic series. That's enough to write for harmonic and alternating harmonic. But if you wanted to write more, you could say that it's alternating, the terms are decreasing, and they're approaching 0. So that's how we know it converges. So that means we include the 7. So that's our radius of convergence. In our interval of convergence, we're centered at 5, so we added 2 and subtracted 2, and then checked the endpoints. So any number greater than 7 and less than or equal to 3, if we plug that in for x, this series is going to diverge. Only numbers in this interval make the series converge, and that's our answer. So that's pretty much the most work you'll ever have to do to find the interval and the radius. There's 2 more examples we're going to look at that are a little bit simpler. So we've now seen an example that had a value r that was finite and not 0. And we've seen how we check to see which of these 4 cases we have. So now let's see what happens if we have a radius of infinity or 0. So we're going to try letter B. All right, so I'm going to jump straight to the ratio test here. So that's what we typically do to find the interval of convergence. So we have a limit as n approaches infinity, absolute value, and I'm going to do a sub n plus 1 over a sub n. So a sub n plus 1 this time. I'm not even going to write the -1 because it's just going to cancel out. So we have x to the 2 times n plus 1 over 2 times n plus 1 factorial times the reciprocal of the original, 2n plus 1 factorial over x to the 2n plus 1. And let's see what happens here. First, I'm just going to kind of distribute those n plus 1s. So we get x to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. And let's see. So on top, let's see what we can do to cancel some things out. We have, if we pull out an x to the 2n plus 1, we're going to be left with an x squared, because I have an extra 2 that I pulled out. And then 2n plus 1 factorial over 2n plus 3 times 2n plus 2 times 2n plus 1 factorial times x to the 2n plus 1. And so I pulled out the first 2 terms of the factorial. And now the factorials can cancel. X to the 2n plus 1s can cancel. So we get the limit as n approaches infinity of x squared over 2n plus 3 times 2n plus 2. And just like in the previous question, I'm going to pull out the n part from the x part. So we have the limit as n approaches infinity of 1 over 2n plus 3 times 2n plus 2 times x squared. So we've got the n portion and the x portion separated, so the limit only applies to the n portion. As n approaches infinity, our denominator is going to keep growing, so that means this is really going to equal 0 times x squared. X squared, when you square something, it's always going to be positive, so I can just drop the absolute value. But that has to be less than 1. So the question becomes, what values can I plug in for x that make 0 times x squared less than 1? And I'm pretty sure I can plug in any x, because when I multiply times 0, it's going to be less than 1. So that means in this case, our r is infinity, and our interval of convergence will be negative infinity to infinity. All right, so there's the answer to that one. That brings us to letter C. And for this one, I'm going to start the same way as before. So we're going to start with the ratio test. So a sub n plus 1. This time we don't have a fraction in our series, so I don't even need to separate this. So a sub n plus 1 is going to be n plus 1 factorial times x minus 3 to the n plus 1. Remember, we don't change the x. On the bottom, we just have the original. And so if I kind of manipulate this so things can cancel, on top we have n plus 1 times n factorial times x minus 3 to the n times x minus 3 over n factorial times x minus 3 to the n. And now the n factorials cancel, the x minus 3 to the n's cancel, and we're just left with the limit as n approaches infinity of the absolute value of n plus 1 times x minus 3. And we could separate this like that. So the n plus 1 portion is going to be approaching infinity no matter what x is. You can see that right here. So we want to know, when is that going to be less than 1? Well, the only time that this is going to be less than 1 is if x equals 3. Because when x is 3, this whole thing's getting multiplied by 0, and this portion in this scenario is stronger, so it takes over and makes it equal to 0. So it only works when x equals 3. So in this final question here, we would say that the radius of convergence equals 0. We can't go above or below our center point. We're centered at 3, so it only works when x equals 3. So our interval of convergence is literally just x equals 3. Our interval of convergence is just one value, x equals 3. And that's it. So now we've seen examples for all of these types of convergence for intervals. We've seen when r is 0, we've seen when r is infinity, and we saw one where there was a positive finite number for r, and how we have to check the endpoints. So that is everything in this lesson. All right, so I know there's a lot going on there. Hopefully that all made sense. Let me know what you think, and I hope you have a great rest of the day. Thanks.